Okay, so this chapter is the introduction to metabolism, and we actually have two chapters about metabolism. And so I'm going to do my best to get these uploaded just as quickly as possible, hopefully, by the end of this weekend. And so that will take care of this week and next week. We're going to start off with the introduction. And so basically, the living cell is basically a miniature chemical factory where you have thousands upon thousands upon thousands of reactions occurring. The cell is going to extract energy from the environment, either from photons or carbon that they eat or something like that, and apply it to somewhere else to perform work. Why is it moving? Okay, so to physicists, the energy represents the capacity to do work. But to biochemists, and in this particular situation, we're going to count ourselves as biochemists. Energy represents the capacity for change. And so cells are going to acquire energy from their environment, and then we're going to go through some information so that you can understand why we have to acquire the energy rather than make energy. So cells cannot make energy, and this is one of the one of the laws of thermodynamics. Cells cannot make energy. Energy is neither created nor destroyed, but it can be transformed. And so in life, energy transformations consist primarily of movement of molecules and changes in chemical bonds. And so you've all heard this before. Excuse me. Kinetic energy versus potential energy. Kinetic energy is the energy associated with motion. And one of the most common kinetic energies is going to be heat or thermal energy, which is kinetic energy associated with the random movement of atoms or molecules as the temperature goes up. And we remember how things move a little bit faster when you heat it up. And so basically you're increasing the kinetic energy when you heat something up. Potential energy is energy that matter possesses because of its location or structure. And so this is the ball on top of the hill, has quite a bit of potential energy, and then as soon as it starts rolling down the hill, then you have just all kinds of changes to a kinetic energy at that point. So chemical energy is also part of the potential energy, and is this potential energy available for release in a chemical reaction. So you can convert kinetic energy to potential energy, but you cannot you cannot just create it out of anything. You can convert potential into kinetic, kinetic into potential, chemical into heat, all of those different types of things. So here we have water moving down a stream. And so this is going to be that kinetic energy. Now, if we stop up right there, that water, that's going to be our potential energy. Our potential energy right there, because you are stopping it from moving. And so that's, it's in a position where it cannot move. That's going to be potential energy. Then we harvest that potential energy in electricity. And so the electricity is transferred on wires and, the telephone wires and things like that, where you can use that energy in several different forms. So now it can be converted into a light energy so that you can light your lamps. It can be converted into mechanical energy so that you can do your fans, or you can, store it in terms of using a battery charger. So this is kind of a neat thing. When your garage is all messed up, this is basically what we call chaos. And so the energy of life is all about trending towards a chaotic environment. And so it takes work in order to get it into an organized environment. And so, your garage beforehand, your garage beforehand is just a very chaotic mess. And then you put in the work to get the garage organized. But I will say that the energy doesn't like that. The environment doesn't like that. It wants to be in that chaotic state. So according to the first law of thermodynamics, the energy of the universe is constant. It can be transferred and transformed, but it cannot be created or destroyed. This is also called the principle of conservation of energy. So you're conserving energy by transferring it and transforming it, but it's not going out, and being lost to the environment. So this is a little illustration showing the first law of thermodynamics. Now, one of the things that you need to remember is that every time you transform energy, you're going to have sections that are lost. You're going to have lost energy. And so that's energy you cannot use. And so you have, your energy before, and then you transfer it or transform it into, say, kinetic energy. You're going to lose a little bit of energy that you cannot get back, because during that transformation, it does, you get a little bit of lost energy. So during every energy transfer or transformation, some energy is unusable and is often lost as heat. And so in humans, when we are losing a little bit of our heat, or that unusable energy, that's our body temperature. So that's that's what keeps us warm, is we're using some of that energy, transferring it within our bodies, and some of it is unusable, and so that's where the heat comes from. According to the second law of thermodynamics, every energy transfer or transformation increases the entropy, or the disorder or the chaos, of the universe. And so, here we have the second law of thermodynamics, where we have the top, we have our energy before, and it's transformed, and now you see you're going to have a little bit of unusable energy after, but you still have a little bit of the usable. After you, the energy before is called free energy. So free energy. That's what this energy before is. And so if you go through multiple transformations, go from kinetic to potential, back to kinetic, and then on to heat or whatever, you're going to lose a little bit of that free energy. And so you're going to have less and less and less free energy, and more and more and more unusable energy. And so you can see here, going from box to box, you can see every energy transformation, we lose a little bit of that free energy. And that free energy, at some point, we're going to run out of it. Now, one of the things that we talk about, and we will be discussing several times, is the free energy is also called, I believe it is called delta G. I think that's right. So delta G. And so we'll be talking about this several times over the next couple of over the next few slides. Oops. All right, so we can have a couple of different types of reactions in that occur without an input of energy. This is going to be what we call catabolic or spontaneous reactions. Catabolic are also reactions where you're going to break something down. And so I always think about cats. And of course, cats like to, push things off of a table and break them. And so a cat is catabolic. It breaks things down. And when you do that, you can also release energy. So just like the breakdown of carbohydrates during digestion, that's going to release a little bit of energy to us. Diffusion, we don't put any energy into there, but we do release a little bit of energy. A ball rolling down a hill, again, that is going to be a catabolic or a spontaneous reaction. An anabolic or a non-spontaneous reaction, or a building reaction, is going to require a little bit of input of energy in order for them to occur. So, if you want to start building muscles, then you take anabolic steroids. If you want to, another thing is if you want to build muscles, but you don't do anything, you just sit on your couch all day, then you're not putting in the energy in order for you to build those muscles. So you're not going to have muscles being built. So examples of this would be increasing the amount of proteins in a muscle cell by repetitious movement with a weight or something like that. Active transport, a ball being pushed or kicked down a hill. These are thrown up a hill. These will all be examples of anabolic or non-spontaneous reactions.